My name is Zhenming Wang. I'm the section head of a geologic hazard section at University of Kentucky at Kentucky Geological Survey. I will present my research. The title is Earthquake Monitoring and Seismic Hazard in the vicinity of the Paducah Gas Diffusion Plant. This is a effort is over the past 20 plus years effort, really funded through the Kentucky Research for Consortium for Energy and Environment. And here is kind of background why we're doing this research. And then you can see here really where's Paducah Gas Diffusion Plant. That's a star here, and Paducah is right here. And you can see that this area is Jackson Purchase of Western Kentucky, and you see the here is so-called pneumatic seismic zone. So you can see Paducah Gas Diffusion Plant really in the vicinity of the pneumatic seismic zone. So that it definitely had a seismic hazard concern. And then what the problem actually back to 20 plus years ago really is when the national seismic hazard map was produced, and then they, based on that, make a mitigation policy. But one of really few things here for Paducah Gas Diffusion Plant area, really first top is about that time is the Uland field seismic design, and it's very high back to year 2000. And you can see here design PGA is 0.8 G, very high. And then you can see here in comparison with the San Francisco, actually Paducah right here as a design number actually slightly higher than San Francisco. And particularly if you look at Paducah, Gas Diffusion Plant actually design is higher than San Francisco. So that's really it's kind of, it doesn't make a good common sense. Say if say Western Kentucky had to do more in terms of earthquake than San Francisco. So that's kind of where the problem coming. And also you can see here back that time Kentucky residential code has a problem. You can see here Jackson Purchase area is very high. It's hot. For residential code, we have considered for earthquake design is higher than San Francisco. And on top of that, there's a lot of economic development because, again, where the Jackson Purchase Paducah area is very active economic development. But due to this seismic hazard concern, so that is where the problem starts. And as soon as we got involved back to 20 years ago, so we really, first thing first, again, in order to do the earthquake research, first thing first, you had to have network, monitor the earthquake, you see where's earthquake occur. So this is a network. We was able to get money, put the network and enhance it. So this is where we start a network operation, monitoring. And then here's kind of over the years, you can see this is we record the monitor earthquake, and plus other network. Here's kind of you can see the seismicity, and then start is Paducah Gas Diffusion Plant. So you can see the earthquake. This magnitude is small magnitude normally, and really high magnitude you can see here is rest 7 point and about. Really that back to 1811, 1812, that we had at least 3 larger events. And then the really thing on the right side, I think of really the interesting, I want to point it out again. This is seismicity from based on earthquake, what we know. And then you can see this kind of trend should be go like this, but this also from geologically, also from we so-called paleoseismology study is quite the bigger difference. So you can see the discrepancy between the earthquake record and the geologic record. So this is where kind of why we had to do more research. Otherwise, it's quite bigger difference. So that's kind of what basic research in terms of network operation. And they want we take a look at the key thing for us here. Need to look at why the policy we are making in terms of earthquake hazard mitigation for Western Kentucky and particularly get why it's so high. And then let's look at process in the United States, how the policy, how from seismic hazard, basically from science to the policy, and also to the local community mitigation. And this is just show you the process. First, USGS, they collect scientific data and make a national hazard map. So this is basically based science. And then a group of engineer, policymaker, and seismology, they came together and look at the hazard map and look at engineering principle, and then develop a so-called a design ground motion map. And then that become policy. And then this policy first, it's really it's federal policy. FEMA, really the group they put together, and then all the federal agency adopt it, and also state agency, like for Kentucky, like become the building code is Kentucky Residential Code, all adopt it. And other organizations also adopt that and becomes all kind of different government agency and different local jurisdiction policy. This is how the seismic hazard mitigation policy be made in each state. So for us, really, we look at why only look at hazard, because our goal is science. Our goal is on the science. And then really we take closer look what the USGS, the hazard map they produce. There is a two common kind of approach to make hazard map. One is a probabilistic, this USGS using. The other one also common people use called deterministic map. So what we did is kind of go look at that at these two methodology, how it's work, what the product they are. And then you can see it's really two methodology use the same data set based on all same scientific information, but to produce a map and communicate different way. That's really the difference is the last step. It's called PSHA hazard map and DSH hazard map, deterministic seismic hazard map. What really would take a look at, take a very close look at, really PSA was developed back to 70s. What really we find out that's problem really there is a basic probability seismic hazard analysis. There is a basic, there's a math problem. What really can show here, if you look at this equation on right side here, this is original development. On the right side is a probability. No, I'm sorry. On the left side is a probability, but on the right side become a frequency. Probability is no dimension, but frequency become dimensional. So this really is a problem. And then if you see on the right side in the paper, you see here probability is no dimension, but a reciprocal probe become a time. So what really communicate is confusing. What really we find is a conflating the annual probability is a probability with a current frequency. So that's where it's a problem. So really miscommunication of seismic hazard. That will we find. Then, so we also look at deterministic analysis. And what we find out, really, you can see here that we produce a deterministic map, and what really how the for our particularly for particular ULAM field, it took, you see here, it took them more than 10 years go through this time consuming communication, everybody finally, I think for landfill, first originally used PSHA, again, the design should be about 0.8 G. After 10 years effort, we finally use the deterministic hazard analysis and also doing a site-specific analysis. You can see here, really, year 2010, that conduct deterministic analysis and then also site-specific, really settle 0.33 G for the new landfill. That's how we help the state fail DOE and resolve the design ground motion issue. Use the deterministic hazard analysis. And also, we was able to work with the state. That time is Kentucky, the Department of Housing and Development, and what we was able to change the residential code category for Western Kentucky, particularly Jackson Purchase area, from E to D2, really eliminate the difficult the construction for residential building in Jackson Purchase area. We also, particularly you can see a Jackson Purchase area, and then this is really have a thick soft sediment. We know when earthquake occur, also we so-called side response. What really means when earthquake ground motion propagate from hard rock through the soft sediment, you amplify. So, and through this research program, we was able to have 2 borehole, put the instrument there. You can see here, this where location, particular defense plan, we have station here called BSAP right at the facility there. And we also do it, it's almost 600 meter this so-called QSO. And then here is the 2 hole depth, the shear wave velocity. This BSAP is about 100 meter. You can see, and QSO is almost 600 meter. You can see the shear wave velocity measurement. And here's our observation. You can how the ground respond. And really you can see so-called side response. You can see certain side at the side frequency, the ground will amplify. So this is what another study we had done. And current, they also building code, like all the rest, the kind of federal regulation use so-called near site class. Basically, they take a 30 meter the shear wave average on top 30 meter. But what we can see for our area, you can see these 2 borehole, 30 meter really doesn't count anything. Really, it's not appropriate. And this is exactly what we find out. This so-called side class, this really cannot account for the side response for the area for the Western Kentucky. So here's kind of what our study has shown. Really, so far, all the federal regulations are based on information is not necessarily correct or it's not adequate for the area for the Western Kentucky. So here's summary. So our research and analysis conduct so far has helped us, again, develop more appropriate ground motion hazard for seismic design and other policy consideration for the particular given plan and the vicinity of the Western Kentucky. And the other thing, clearly, our research, our research will benefit not only for particular gas defense plan, but also for Western Kentucky, as well as the Commonwealth of Kentucky. That's all I have. Thank you.